I think we're good to go.
Okay, so welcome everybody to today's math club. I'm here today to talk to you just about a problem generating functions that I really like. I'll start off by talking about a dice problem that sometimes is attributed to his name is Mosteller. He was a staff professor at Harvard many years ago. I'm a big fan of this undergraduate probability book by Joe Blitzstein and Jessica Wong. And the probability problem I talk about is from that book. And they attributed to Mosteller this whole story and everything. I'm sure he didn't come up with it. It's a pretty standard problem. So I'll talk about that and how you can solve that generating functions. And then after that, I'll spend the rest of the time talking about a really neat trick for numerically inverting a probability generating function. It comes from a paper in the 90s by some black problems. But it's very elementary. It only involves just the basics of complex variables. So if you understand the roots of unity, you're pretty much good to go. There we go. All right, so what is a generating function? So basically, a generating function is a type of mathematical object that you can use to study properties of a sequence of real numbers, or say a sequence of complex numbers. You can shoot this. As you can see up here, we've got a sequence of real numbers A sub n for all of them greater than or equal to 0. And we use that sequence to define this generating function in script A of C, which is defined in this way, so it's basically a power series. We have this power series defined in an open disk of radius r. So obviously you all know that r is the radius of convergence power series. When you take calculus 2, the standard freshman calculus course, you learn about things like that. And in this talk, we're mainly going to be interested in sequences of real numbers that are bounded. So here we'll have a constant c strictly greater than 0, such that this serves as upper bound for the n terms. When you have something like that, you can show that the series is absolutely convergent whenever c is strictly less than 1. So the radius of convergence is going to be at least 1. Okay, throughout. Questions so far? Yeah. All right. So one thing that's nice about generating functions is there's a one-to-one correspondence between a sequence of real numbers and a generating function. So it's really straightforward to see that if you have a sequence of real numbers, you can use that generating function. That's obvious because that's how you define the generating function. But you can go the other way too, and you can show that just by playing with derivatives. So one nice property of power series is that as you take derivatives of a power series, you get other power series that have the same radius of convergence. It's a very elegant property. When you take a course in complex analysis, that's the basic idea behind understanding what a function is differentiable on a complex plane. So as I take a higher order derivatives, the kth order derivative of the generating function evaluated at z is equal to this guy. Again, I know the radius of convergence is at least 1 if the original radius of convergence is at least 1. And if I evaluate the kth derivative at 0, I get this guy, so that turns out to be k factorial times ak. So we basically showed that if you want the kth term in the sequence, that's equal to the kth derivative of the generating function evaluated at 0 divided by k factorial. Now again, if you study Taylor series, that's kind of obvious because basically this is the sort of thing you see when you study the Lorentz series expansion at 0, right? That's redundant. Lorentz series expansion, so Taylor series at 0, right? So that's why there's a one-to-one correspondence between generating functions and their sequences. So as a probabilist or applied probabilist, you learn about other things like moment generating functions. So a random variable, the distribution of a random variable is determined by its moment generating function. The idea is analogous to what's going on here, except it's a little bit harder. Of course, not every random variable has to have a generating function, but everyone does have a characteristic function, and there's a similar one-to-one correspondence between distributions and characteristic functions. This is just the most elementary version of that basic idea. Okay. All of you hopefully know this identity. So one type of identity we're going to play around with is not only the standard geometric series, but also negative binomial series. So if you look at this first series, we've got the sum from n equals 0 to infinity of z to the n. You can assume z is complex, and whenever the modulus is less than 1, modulus being the length more or less of the complex number, the sum of z to the n is equal to 1 over 1 minus, right? We all know that. A lesser well-known identity is the following though. So if you look at a series of this form, you can show that the radius of convergence of this series is at least 1. And for every z satisfying the property that modulus is strictly less than 1, this sum turns out to be 1 over 1 minus c raised to the power k. And this is a very useful identity because for a lot of reasons, and we'll see why it's useful in our dice example. Hopefully you all know this notation. So n choose k, of course, is n factorial divided by k factorial times n minus k factorial, right? Right. If you want to prove something like this, basically the idea involves realizing that if you look at, actually I think it's on the next slide. So if you're wondering where that previous identity came from, the idea follows from the following. Suppose I have two sequences, a sub n and b sub n of, say, complex numbers. I said they were real numbers at the beginning. They can be complex. It doesn't really matter that much. So if we have sequences of real numbers or complex numbers with generating functions a, b, and then for each integer n greater than or equal to 0, we let Cn denote basically this term right here. So this is a convolution term, right? And you can show, it's pretty straightforward, you can show that the generating function satisfies this property, right? So C of C is equal to A of C times B of C. We're not going to worry so much about radii of convergence here because when we apply this idea, the radius of convergence of both of these are going to be the same. So this is going to have the same radius of convergence. So don't worry so much about that. So this is the basic idea. So if you go back to the previous identity, you can show this basically, one way to do it is by induction. It's obviously true whenever k is equal to 1. So this is an identity that's true for each k greater than or equal to 1, each positive integer k. In the case where k equals 1, you just get standard geometric series. And then you can assume it's true for k, and then prove it for k plus 1. Basically, the idea is writing down that convolution term, use the well-known hockey stick identity, right, which you all have learned about in combinatorics. And that, along with interchanging sums and playing around with those kind of tricks, give you this identity in general. There's also, I'm sure there's all sorts of ways you can show this. But that's one way. Yeah.
I've not heard of the golden hockey stick theorem.
Yeah. So basically, you've got if you look at Pascal's triangle. What it more or less says is if I add up these numbers, I get this number. 1 plus 2 plus 3 plus 4 is equal to 10. Likewise, I can do the same thing anywhere. If I add up these three numbers, I get 15. 1 plus 4 plus 10 is 15. And it kind of looks like a hockey stick. So you're obviously not Canadian. I could resist. Right. So this is the basic idea behind the hockey stick idea. And I think it looks something like what is it? Sum L from K to N of L choose K. It's going to be N plus 1 choose N plus 1. That's the actual form of the hockey stick identity, but I find this a lot more understandable. It's the same idea though. Any other questions about that? So this is what's involved when you're trying to establish this result using induction. And you can, induction arguments are always sort of lacking because they hide, the nuances behind where the idea really comes from. But this is a situation where, you can work out the case when k is equal to 2, and you see the pattern pretty quickly. So the induction argument is still pretty satisfying, at least that. Okay. All right. Yes, I've already talked about that. So I guess I should probably, before I get into the dice problem, I should probably write down that identity. So we said that for each integer k greater than or equal to 1, I'll look at the sum from n from 0 to infinity. N plus k minus 1, choose k minus 1 times z to the k this thing is equal to 1 over 1 minus c to the power, oh, sorry, to the end. 1 over 1 minus c to the power, okay. We'll make use of that shortly. So this is the negative binomial sum, just so you can have that for reference. Okay. Right, so here's the dice problem that I was referring to. When you take, a course like Math 4000 or a standard undergraduate course in probability or statistics, the first thing you talk about are sample spaces, outcomes, events, that sort of thing. And you probably also see problems that involve things like, if I take a fair six-sided die, I roll the die, I obviously see the number 1, 2, 3, 4, 5, or 6. Yeah. And I'm equally likely to see any one of those numbers. So if x1 is a random variable representing the outcome of that die roll, the probability x1 equals 6 is simply 1 over 6. Obvious, right? There's 6 possibilities, they're all equally likely, therefore it's 1 over 6. Well, what if I take 2 fair six-sided die? In that case, you can pretty reasonably argue that every outcome should be equally likely to occur. So if I roll those 2 die, I can get, die 1, assume it's colored blue and the other one's colored green, I don't know. Die 1 could be 1, die 2 could be 6, all sorts of different possibilities. You can set up the set of all possible outcomes as ordered pairs, right? And there's 36 of them. They're all equally likely to occur. It's pretty reasonable to assume. Again, it's a model. Technically it's not reality, but it's pretty good. And if you follow that model and you roll the 2 die, the probability that the sum of the 2 numbers is equal to 8 is going to be 5 over 36. And you can figure that out just by enumeration. In other words, you can just write down all the possibilities, figure out which outcomes correspond to a set of 5. The number of such possible outcomes is 5. The number of total outcomes is 36. So ergo, you get 5 over 36, right? But things get a lot more interesting when you start making the number of die you roll a lot bigger. So, like, for example, what if I roll 4 six-sided die, right? So in the top here, it says, what is the probability that if I roll 4 fair six-sided die, I observe the number 13? Well, that's a tougher problem because now, if you try to use enumeration, there's going to be 6 to the 4th or 1,296 possible outcomes. So you'd have to look at every one of those outcomes and decide whether or not you get a sum of 13, right? And I'm not a combinatorics person. I mean, there might be really tricky ways of doing this, but I don't know of a counting argument you can use to solve this in an elegant way. So it turns out, though, that you can use generating functions, okay? So how would you go about using generating functions to solve something like this? Am I going too fast? I feel like I'm going, no? All right. So basically the idea is the following. Now, probably some of you have seen some probability and some of you haven't. So I'm going to make use of this one fact that you can basically take for granted if you've never seen probability. So if I look at the expected value, again, you don't know what probability is. Some of you don't, so you don't know what this is, but this is the idea. This is the generating function of the sum of the die 1, sum of die 1, die 2, die 3, die 4. These 4 random variables are independent and identically distributed. So if I want the generating function, this is going to be equal to the expected value of C x1 raised to the power 4. But only by independence, combined with the fact that they're independent and identically distributed. But on the other hand, by the definition of the fact that this is a probability generating function, this is the sum from L, I guess, equals 4 to 24 of probability x1 plus x2 plus x3 plus x4 is equal to L, like that, and then I'm multiplying that by z to the power. So ergo, this is a generating function, right? Technically, this is a probability generating function because now in this case, my ANs are ALs, and AL represents a probability. So we're trying to pick off the terms in here, the terms associated with this generating function. and using probability theory, this is equal to this. This is literally what this represents. And then using probability theory, I know that this is also equal to this. And this guy is something I know. Like, so this is just a generating function of x1. And this is going to end up being equal to the sum L from 1 to 6 of 1 over 6 times z to the L. And then I have to raise that to the power 4. Everybody see that? You might wonder where the 1 over 6 comes from. This is the problem. This represents the probability x1 is equal to 1. So if I roll the die, I get 1. It also represents probability x1 is equal to 2 or 3 or 4. So we get that. And of course, I can pull out the 1 over 6, raise that to the 4th power. Oh, I talked about it here. So this is the generating function of rolling a single die. So you end up getting this. And because of that, if I want to pick up this probability, remember this is the probability that when I roll the 4 die, I get a 13. So if I want to pick that off, I just take the generating function associated with the sum, and I pick off the term next to z to the power 13. That's the idea. Okay. So if we look at this generating function, basically we have this guy, and what we want to do is we want to invert this analytic, and this is where this guy is going to come into play. So we are interested in looking at z to the power 4 divided by 6 to the 4, which is 1296, times I've got a 1 minus z to the 6 raised to the power 4. Then I've got a 1 over 1 minus z raised to the power 4. Now, all of these things look nice. Number one, I've got a z to the 4 over 6 to the 4. That's a very well-behaved term, right? From the point of view of trying to capture the generating function I'm actually interested in. This term is pretty harmless too. I can expand that with the standard binomial formula, right? And you get another polynomial. The troublesome term is this, but thankfully, I can use this idea. So this is where I'm going now, right? So now I end up with what looks like an infinite series consisting of coefficients times z to the, to the n, if I'm summing over n. So when I write everything out, this is what I get. So this is my generating function. I expand, I write everything out. So now the game is basically interchange this sum, do a little bit of manipulation. Actually, you don't even need to do that. You just need to, at this point, look for the terms that are next to a z to the power 13. And when you do that, you end up getting 1 over 6 to the 4 times this. So the final answer with generating functions is the probability that the sum of the 4 rolls is 13 is 140 divided by 1296. So again, there's 140 different outcomes you need to take into consideration. And the form of this suggests that there's probably, if there is a counting argument, it's probably fairly complicated, right? You can do this for other cases. As a matter of fact, one thing you might be wondering is, I just said that this is another representation for this generating function, but you might be a little puzzled about that, right? Because this is the generating function, or this generating function I know is also equal to this guy right here. This is obviously a finite sum. But if I look over here, there's an infinite number of terms here. So that might look weird. What's going on? But if you think about it for a second and you look really closely at all of the coefficients next to z to the n for n greater than or equal to 25, you can convince yourself of the fact that every single one of those coefficients is equal to 0. To be honest, I didn't formally check that. I checked a few, and I know it's going to work, but yeah. So I did check a couple. So if you check the coefficient in front of z to the 24, we know it's going to be 1 over 6 to the 4. Obviously, only one way to get a 24 when you roll 4 die. When you use that complicated method I had on the previous slide, the coefficient looks like this. Again, this also suggests that there is a counting argument. It's probably pretty crazy. So this guy turns out to be 1 over 64. Verify that. And then if you look at the coefficient in front of c to the power 25, it turns out to be 0. And you can play around with the others, you're going to get zeros from 25 on up. So hopefully from this example, you can appreciate, why generating functions can be a very useful thing to understand and be somewhat familiar with, right? Not only that, what I like about this topic is so many basic ideas from analysis are connected to power series. So that reason alone should be enough to convince you to learn more about this stuff. Also complex analysis, complex variables, so many things involve that. So, okay. Right, now I'm going to shift gears for a minute and consider another type of problem that I think on the surface probably looks a little bit artificial, but there's a real reason why you'd actually be interested in problems like this. So the problem is the following. Again, we've got a sequence of real, you can assume the numbers are real, they could be complex, but it doesn't matter. Assume the numbers are real. We're going to assume that the supremum of the absolute values is less than or equal to c, some constant c, i.e. the numbers are bounded, again. And script A is going to denote as generating function. And what we want to do is we want to evaluate the following series. So I know that A of z is equal to the sum over n of A of n times z to the n. But I'm going to look at what happens if I sum over some of the terms instead of all of them. So I'm going to fix an integer m greater than or equal to 1. And I'm going to fix an integer nu in the set from 0 to m minus 1. And I'm going to look at this following series. So I've got the sum from n equals 0 to infinity, a of m times n plus nu times c to the power mn plus nu. What am I really doing here? I am looking at summing over all indices or all positive integers that are divisible by nu. When I divide by m, the remainder is nu. Excuse me. So I'm summing over all non-negative integers such that when I divide by m, the remainder is nu. Right? As a fun example, if all of these a's represented probabilities associated with a random variable, if you can evaluate things like this, you can calculate things like if I take a Poisson random variable, what's the probability that when that Poisson random variable is equal to a number divisible by 8? Or what's the probability that when I take that random variable, that number is equal to a number that when I divide by 12, I get a remainder of 5. These are the sort of probabilities you calculate if you can get a handle on these types of series. But I'm going to go beyond that. I'm going to show you how you can use these type of things to actually perform numerical transfer conversion or numerical generating function conversion. Now, a special case of this is probably something you've seen before. If not, it's easy. So instead of summing over something like this, what if I were to look at a simpler construct? What if I were to sum over only the even integers? So instead of looking at the sum of a and z to the n for all n greater than or equal to 0, I'm looking at a0 times c to the 0 plus a2 times c squared plus a4 times c to the 4th, et cetera, et cetera, et cetera. How would I get that? Well, there's a very simple trick involved in getting that. So the main thing is to realize that I should take the generating function and evaluate it at negative c and also c. Now look at what happens when I do that. I've got up here in the top sum, I've got a negative 1 to the power n times c to the n. Then down here I have basically a 1 to the n times c to the n. So when I add these two things up, I get a lot of cancellation. And I end up with this sum being 2 times the thing I actually want. So in other words, if I want to evaluate the series, this is equal to this guy. Again, I'm looking at z satisfying the property that the modulus of z is less than 1. So, right? Makes sense? Okay. So we can sum over all the even integers, even non-negative integers. You could use the same idea to sum over the odd non-negative integers. All this is going to work. All right, but what happens if I want to look at the other types of sums? Well, here this is mainly for me. When you basically make use of this observation, what's really going on is to realize that when you derive this, in order to get the sum, you basically realize that -1 to the power n plus 1 to the power n is equal to 2 if n is even, or it's equal to 0 if n is odd. Okay. So, yeah, so that's the idea. Okay. Now, what we want to do though is we only want to sum over more restrictive sets of integers. Okay. So, in order to do that, we're going to go back to this familiar geometric sum identity that hopefully all of you know. So if I look at the sum from L equals 1 to M with C to the power L, as long as L is not equal to 1, I get this guy. If L is equal to 1, I'm just going to get M, right? And if you look really closely at what we've got here, look at the numerator. In the numerator, I've got a Z term. That part isn't all that important. It's got to be there, but it's not important. The important bit is realizing that we've got a 1 minus C to the power M term. So we're going to try to take advantage of that when we're looking for ways of when we're looking for ways of summing over those integers that we want to capture, right? So I know some of you know this, probably a lot of you know this, but anybody remember what the roots are of C to the M equals 1? What the solutions are of this? No? They're called the roots of unity. So this is, in fact, probably one of the things you learn about in a complex variables course on, I would guess, the first week. So what are the roots of unity? If I take the complex plane, this is the real axis, this is the imaginary axis. Okay, I'm going to draw a circle of radius 1. Looks like that. And if I draw the roots of unity, for example, there's only one solution to z equals 1. It's right here. There's two solutions to z squared equals 1. It's this guy and also -1. But if I want the roots of the solution to c cubed equals 1, well, I have to move to equidistant points on the circle, right? So I have to go 120 degrees to this guy. This is a solution. I've got to go another 120 degrees to this guy. And then I move another 120 degrees, I get back to the 1 guy. So these are my three solutions to z cubed equals 1. If you want the solutions to z to the 4th equals 1, it's the same idea. Now we're taking 360 degrees divided by 4. So we go 90, 180, 270, 360. So the roots of z to the 4 equals 1 are here, 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 here. If I want the roots of z to the 5 equals 1, take 360 divided by 12. Wow. Take 360 divided by 5, and that's going to be whatever that is. So that you go equidistant, like 72 of this. And so you go 72, another 72, there's 5. 5 equidistant points on the circle. You get the idea. Fortunately, there's a nice formula for this. If you want all solutions to c to the m equals 1, you've got zk is equal to, let's see, this is going to be e to the I over m, e to the I k 2 pi divided by m. Or k. You could use k from 0 to m minus 1, but we're going to use k from 1 to m. If I plug in k equals m, I get e to the I 2 pi, which is 1. Okay. It turns out it's a little more useful to do this way instead of 0 to m minus 1. It's not a big deal. Yeah. So these are the solutions for the roots of the solutions of this equation. You all know what this is, right? If I look at e to the ix, I know this is aimed toward undergraduates. Okay, so this comes up in differential equations. If you look at e to the I theta, this is cosine theta plus the imaginary unit times sine theta. So once you have that, I'm just replacing theta with k 2 pi over m. That's all I'm doing. Right. Okay, so these roots of unity are going to be very useful, and you'll see why in a second. So yeah, so here's the answer. Like I just said, the solutions of the roots of unity. So ZMJ is going to be e to the I times 2. I don't know why I wrote it that way, so it doesn't matter. EI 2j pi over m. It's what I said a second ago. Okay, let's stop there. All right, so let's play around with that finite geometric sum, and let's plug in different solutions to the roots of unity. So if I look at the sum from L equals 1 to M of Z and K to the power L, plug that in, I get this guy right here. Now, if K is not equal to M, so if K is anything from 1 to up through N minus 1, that number is not equal to 1. It's somewhere else on the circle. So if I plug that into my numerator, I get 0. And I can't plug it into the numerator because it's not equal to 1. That's perfectly legit. So this is 0. Otherwise, if I let K be equal to M and plug that in, this is 1, so I just get M. So what we've actually showed is the following. Again, it's very elementary, right? Couldn't get more elementary. This is called an indicator function. Analysts like to call these characteristic functions, but probabilists call something else characteristic functions. So it's funny. I guess not funny, but analysts and probabilists, both rely on measure theory quite a lot, but we have different languages for the same thing. If I use the word characteristic function, an analyst would think of a Fourier transform. Likewise, they call something like this a characteristic function. I would call this an indicator function. So bear that in mind, all right? If you're an undergrad, yeah. Anyway, what is it? What is this? It's an indicator function. This is equal to 1 if the statement inside is true. Otherwise, it's equal to 0 if the statement inside is false. So it's Boolean variable essentially, right? It's either equal to 0 or 1. So all we're saying is if I take each integer nu, given a fixed integer m greater than or equal to 1, whether if I want to write down the expression for the indicator that nu divided by m is an integer, that turns out to be equal to the sum. Now you might look at that and think, how is that remotely useful? Well, we'll see why in a second. So we have this sort of geometric sum-like representation for this indicator function. Because remember what we're trying to do. At the beginning, I said I wanted to sum over all terms of the form amn plus nu times z to the power mn plus nu. And I'm summing over n, right? So I'm only trying to catch the sum over integers where when I divide by m, I get a remainder of nu. And this is going to help me do that. That's why I'm pointing this proposition out. So if I go back now to my original problem, I claim that this sum, the thing I was interested in, can be expressed as this finite sum. And there's no typo here. This is z of L times z. So this is the Lth root of unity. So this should be an mk instead of a k. And right, so we get this guy. And the proof basically is simple. It involves realizing that if I take this sum right here, all I'm doing is I'm summing over all the integers of this form, such that again, when I divide them by m, I get a remainder of nu. Well, after a bit of thought, you can realize that this is equal to this. So this is a fancy way of summing over this. But now I'm summing over all non-negative integers again. Now the idea is take that indicator expression that I had in the previous slide, replace it with that finite geometric sum. You've got a double sum, and solve the sums without problem. Then evaluate that, and you end up with this. Some of you, well, the undergraduates have probably never seen this, but there's a topic called discrete Fourier theory, and this is the basis behind, elementary discrete Fourier theory. I think that's what's going on when you look at compact discs and things like that. I'm not an expert, but that type of math is used in most settings, I believe. You can look it up on Wikipedia or Google or whatever. But anyway, that's really what's going on here. So, like I was saying, if I have a sequence of real numbers a of n, and let's say they represent probability values of the probability mass function, then if I have a non-negative integer value random variable, call that capital X, and I want to find the probability that x divided by 7 has a remainder of 2, I know how to calculate that. Assuming I know its generating function, I can write it like that. So you can actually write down a pretty elegant expression for probabilities of that thing. Oh, you might worry about the fact that I said z equal to 1. That's perfectly fine because we know that because these represent elements of the PMF with a non-negative random variable, signature value, these things will sum to 1. And none of the mass escapes to infinity, so everything's on the line. Okay, yeah, so you can find probabilities that are like that. What about numerical transform inversion? So back at the beginning of the lecture, I told you that there's a one-to-one correspondence between real numbers and their generating functions. And I used derivatives to establish that one-to-one correspondence. So in principle, what you could do is if you wanted to figure out, say, the a nu term, if I wanted to pick off a nu from the generating function, I could take the nth derivative of the generating function. Yeah, take the nth derivative, set it equal to 0, divided by nu factorial, that would be a nu. But from a practical perspective, that can be problematic because when you're taking higher order derivatives, using software, issues can come up. Well, there's ways of getting around that. Here's one possible way. So what I want to do is, my end goal is to somehow use this idea to come up with a way of not only estimating a nu from the generating function, but also come up with a way of estimating a nu where I can control the error term. Okay, is that clear to everybody? So what I have now is I have this original sequence a sub n. Assume I know its generating function, and I want to extract from that a nu. Say I need that to answer some question, the a nu term from that sequence. And I claim that I can use this fact to come up with a pretty good estimate of a nu. And this is the fact I proved a second ago. If I sum over all the non-negative integers that give a remainder of nu and I divide by n, this sum is equal to this. I'm going to use this to get a nu, or at least an estimate. So this is how it works. The idea basically involves, so I've got I know a nu times z to the nu is a term that appears in, should have put it on the slide. A mu z to the nu is the first term in this series. So I can split this up as the idea basically is the following. I apologize to anybody watching this on Zoom. It's been a while since I gave this talk and I forgot I have to write a lot of board, so sorry about that. So I've got, let's see, I know that a nu times c to the nu plus the sum from n equals 1 to infinity of a mn plus nu. C mn plus nu. This guy is going to be equal to 1 over m times sum from what? L equals 1 to m of C ml to the negative nu times a from C M L to C M L times C. You get the idea. So that's what we're doing. And what I want to do is I want to basically divide throughout by z to the nu. So when I divide throughout by z to the nu, I'm comparing a nu with this guy right here. So if I look at a nu minus this, take the absolute value of that, that's equal to minus the absolute value of this, where I divide by z to the nu. So that's what's going on here. Make sense? So this is the thing I'm interested in. This is the thing I can compute because I know the roots of unity, I know the generating function. That's equal to that. Now I'm just going to apply very elementary ideas. So you've got standard triangle inequality. You can upper bound these terms by c. I've got a nice geometric sum. So this difference, this absolute value term, or this modulus, is equal to this guy. And now what I want to do is I want to basically choose C small enough so that the difference between the exact answer and my estimate, my approximation, is less than or equal to some epsilon, some tolerance, some amount of error I'm willing to put up. So that's the idea. You can, maybe I did this wrong, maybe I didn't. It's been a while since I did it. You can quickly sketch what the right upper bound is. So if you pick C, satisfying this inequality up here, I believe that's going to be true. But even if this isn't right, you get the idea. So in other words, you can control the error. So basically, this term right here turns out to be a very nice estimate for A B. And you might have to be a little bit careful if C is too close to 0 because you're dividing by something really small. But other than that, this works surprisingly well for transform inversion. This idea actually surprisingly came from a paper that's, I guess, 30 years old, so it's definitely not a new paper, but they present the same method in this paper that was published in 1992. The method's a bit obscured there, though, because they use complex integration. And I think the reason is because they were looking at a harder problem first, where they were trying to invert the plus transforms of functions. And then they realized, well, if we can do that, why not play around with generating functions to see what happens? If you look really closely at what they're doing, you can move things around a little bit and realize it's all discrete for you. And it's all elementary, right? Every step here was pretty much basic calculus and complex variables. So this is the idea. If you want to learn more about generating functions, there's a ton of references out there. Very popular one that I believe is still free online is Generating Functionology by Herbert Wilf. I haven't looked at this in a long time. Yeah. So perfect. So it's a very well-known textbook. There's plenty of others out there, I'm sure. So yeah, and I had the website here. I forgot about that. It's 5 years ago. You could go to this website. I haven't checked this. These slides are 5 years old. So surf beware, so to speak. But yeah, or you can buy a copy of the book. All right, I think that's basically it. Yeah. So that's all I've got.
Questions?
So I guess I don't ever teach complex variables or complex analysis, but I think this is a pretty good plug for complex analysis. If you're an undergraduate math major, complex variables is one of those courses. I don't think it's a requirement in our program, but I never took a complex variables course, and I wish I had. That's a topic that is used in so many different areas of math and engineering, and yeah. If you have an opportunity to take complex analysis, I don't care what your emphasis area is. That's a course you can. And I'm not saying that for selfish reasons. I never teach the class, so I'm just pointing out that is a ideal course to take if you ever. So
I'm on the pure side of the spectrum, and I agree with that comment wholeheartedly. It was actually required of all the engineer undergraduates where I was.
Yeah.
And it wasn't required of math, but I took it anyway. It is freaking magic.
Yeah.
So ironically, complex analysis makes things easy. So I'll encourage that.
It's common course too.
Yeah.
yeah, sure.
Other questions, comments?
And that's a good point. Generating functions occur in combinatorics, all sorts of different areas. So yeah, keep that in mind.
All right, let's take our speaker. Well, stay tuned for next week. If there's any piece of the rule back